Okay, in the last video, we had integrated the hyperbolic secant cubed of x, and we did it using integration by parts. And we want to see if that same approach will work for this integral, where instead of having the hyperbolic secant, we have the hyperbolic cosecant cubed. And we're going to try and follow the exact same formula as we did before, writing this like squared of x times the hyperbolic secant of x dx. Not using any hyperbolic identities in here, just breaking it up. And remembering now that the integral of u dv equals uv minus the integral of v du. And here's where we have to be careful now. If we're going to use this approach, what are we going to call dv? Because clearly, if I call something dv, I have to be able to integrate it to get v. So that's one concern. The other concern is that if I can, for example, call this dv, if I can integrate that to get v, or if I can call this dv and integrate to get v, which one gives us the simpler expression? So, if, for example, we call this dv, then v is something like the natural log of the hyperbolic tangent of x over 2. It's one of those weird expressions. Well, I can find that easily enough, but then when we use our formula here, we're going to have this stuck inside of the integral side, and now we've got to try to integrate this. Good luck. So I don't think that would be a wise choice. So we abandoned that approach. And say, well, let's try with calling this dv. So if we do that, and we say let dv equal the hyperbolic cosecant squared of x, then v, that's just minus the hyperbolic cotangent of x. That's much better than what we had before. So clearly this would be dv, and then this is u. So we say let u be equal to the hyperbolic cosecant of x, then du, that's minus the hyperbolic cosecant times the hyperbolic tangent dx. So if we go this route, then what are we going to have? We've got the integral of the hyperbolic cosecant cubed of x dx equals u times v. This is u and this is v, so we're going to have minus the hyperbolic cosecant times the hyperbolic cotangent, times the hyperbolic cotangent of x, minus the integral of v du. Negative, negative makes this a positive, so now we're going to have, so this negative sign holds, so now we're going to have the cosecant times the hyperbolic cotangent square root of x. dx. And then here then is when we want to start thinking about hyperbolic identities. The hyperbolic cotangent squared of x, that's equal to 1 plus the hyperbolic cosecant squared of x. And this has a minus sign. Okay, this might set us up all right. Look what's happening here. If we use this substitution here for the hyperbolic cotangent, then we have to multiply by this. So we're going to get the integral of the hyperbolic cosecant. That we know how to do. This is a minus sign, minus the integral of this times this. That would be the hyperbolic secant cubed of x, which we could take over to this side. So this should work out okay for us. We have, this will be equal to minus the hyperbolic secant of x times the hyperbolic tangent of x minus the integral here, multiplying through, that's minus the integral of the hyperbolic cosine of x. And then here we're going to have minus the hyperbolic cube of x dx with the minus sign, so we'll take it over to this side, and now we're going to have 2. Okay, and let's see. So we're going to get then the integral of the hyperbolic cosecant cube of x dx will equal, dividing through by 2, we're going to have minus hyperbolic cosecant of x times the hyperbolic cotangent divided by 2, and then this is going to be minus 1/2 dividing through by 2, the inverse sine of the hyperbolic tangent of x over 2 plus an arbitrary constant. This dividing through by 2 here. And this integral here, it's one of these weird ones, remember. You have the inverse sine of the hyperbolic tangent of x over 2 plus an arbitrary constant here. And that would pretty much take care of that. And again, if this was to the power n, where n was 3 or greater, we should be able to use integration by parts here to solve this to any power where n is 3 or more, 3 or higher. So, okay, that's it for this video. Come back and join us for some more videos, and we'll see if we can solve some more problems.